Section 4.3, Implementing Ontologies in Neo4j. How to translate OWL concepts into the labeled property graph model, and how to use the neosemantics plugin to import RDF and OWL directly. OWL and RDF represent the world as triples: subject, predicate, object. Neo4j's labeled property graph represents it as nodes with labels and properties connected by typed relationships. The two models are different, but the mapping between them is mostly intuitive. An OWL class becomes a node label. The class drug in OWL becomes the label drug in Neo4j. Straightforward. RDF type, the OWL statement that assigns an instance to a class, becomes label assignment in the LPG. When aspirin is declared RDF type drug in OWL, in Neo4j, aspirin gets the label drug on its node. RDFS subclass of, the hierarchy relationship, gets stored as a relationship between class nodes. You'll typically see this as a open parenthesis, small molecule, close parenthesis, dash open bracket, SCO, close bracket, arrow, open parenthesis, drug, close parenthesis, relationship, where the class nodes themselves become nodes in your ontology subgraph. OWL object property maps directly to a relationship type. The treats property becomes the treats relationship type, connecting drug nodes to disease nodes. OWL data type property maps to a node property. The approved date data property becomes the drug.approved date property. The one place where the mapping gets complex: OWL restriction. OWL restrictions say things like, drug treats at least one disease. Neo4j has no native enforcement for this. You handle it as a constraint through cipher or store it as metadata on the property node. This is the main expressiveness you lose in the OWL to LPG translation. The neosemantics plugin, also called N10S, short for neosemantics, is what makes it practical to work with RDF and OWL inside Neo4j. Without it, you'd have to manually transform every triple into a node or relationship. With it, you can import a complete ontology in a single cipher call. What does it do? It imports RDF data directly into Neo4j, supporting the four most common RDF serialization formats: Turtle, RDF/XML, JSON-LD, and N-triples. It handles namespace prefixes automatically, mapping them to Neo4j label conventions. And it goes the other direction too. It can export your Neo4j graph back to RDF, which means you can expose a Sparkle endpoint on top of Neo4j. Let me walk you through the basic workflow shown on the right. Step 1. Initialize the graph for RDF with call n10s.graphconfig.init. The handle vocab URIs setting tells n10s how to handle URI prefixes. Map means map them to short names. Step 2. Create a uniqueness constraint on the resource URI. This prevents duplicate imports. Step 3. Import your ontology with call n10s.onto.import.fetch, passing the URL and format. If you want to preview what would be imported without committing, use n10s.onto.preview.fetch first. After import, your ontology classes are available as class nodes in the graph, and you can query them with standard cipher. This is how you'd import SNOMED-CT, CHEBI, or FIBO. all of which publish their ontologies in standard RDF formats. One command and their entire class hierarchy is inside your Neo4j graph. One of the things that surprises teams when they first build a production knowledge graph is how often the ontology needs to change. Domain understanding deepens, business requirements shift, external standards get updated. You need a strategy for evolving your ontology without breaking everything downstream. Strategy 1. Version numbers on ontology nodes. Add a version property to your class and property nodes. Queries can target a specific version or always retrieve the latest, using order by on the version field. Strategy 2. Named graphs and subgraph separation. Store each ontology version as a distinct subgraph, labeled with a version identifier, ontology v1, ontology v2. Old and new versions can coexist in the same database, and migration can happen progressively. Strategy 3. Deprecation rather than deletion. This is the most important one. Never delete a class that has instances in your graph. Add a deprecated property set to true and create a replaced by relationship pointing to the successor class. This preserves the historical integrity of your instance data while signaling to downstream systems that the class is no longer current. Strategy 4. Model changes as graph nodes. Create a change node for each ontology modification, recording who made the change, when, and which classes were affected. This gives you a full audit history, directly queryable in Cypher. The golden rule. Ontologies are contracts. Breaking changes break downstream systems. Always deprecate, never delete. Version early, version often.